parse ambiguity, grammatical clause.
I could share my. Oh, I could. Yeah, I just added my file slides to the chat. Can people hear? Hopefully, I can share my screen.
You're not sharing your slide.
I'm not showing my slides. Oh dear. Hold on. No, I want to share my screen. So if you're seeing my screen, then that's actually what I want to share. You're seeing my screen?
Yes.
Ah, then these are my slides. Sorry, I'm not in the right directory. I'm so prepared for this talk. Okay.
Can you pop up first a bit? Yeah. Can you make the?
Yeah, okay. I can make it bigger. Yeah. Yeah. Sorry, this is a Vim presentation. Okay, so I can begin. Yeah, I hope. Yes. Okay, so I'm going to be talking today about constraining parse ambiguity with grammatical codes. And my name is Alastair Butler. I'm working at Hirosaki University. So here's the introduction that I have. So the talk is going to introduce a wide coverage toolkit for obtaining full parse analysis for English sentences. Well, when I say toolkit, the reason why I'm using toolkit is because there's a series of components which contribute different parts towards reaching analysis. One of those parts is a parser, which I'll be focusing on mainly today. Another part is a semantic calculation of the parse results that will give different perspectives of the semantic calculation that the overall toolkit can give. Again, is another perspective on analysis. Well, I'll talk about the purpose. It's very much a kind of a tool that I want to create to help me teach my students about techniques of language analysis. And so I teach students who are medium to advanced learners of English, and I want them to know more about the structure of English. And I think teaching them about parsing is a good strategy for doing that. The parse results that the parser that I'm going to talk about produces. This is the analysis is going to follow this tree bank called Tree Bank Semantics Parse Corpus, which is available online at this URL. Yeah, I can quickly open that up. So here's the front page that tells you, and there's a search interface for exploring the data set. Well, anyway, that's the target of the analysis. So what do I mean by full parse structure? Because that's I want a parser that's going to produce this. By full parse structure, I want labeled constituent structure. So that's going to be essentially bracketed nodes that are going to tell me about the types of constituents that are being built. So these are going to be things like matrix clauses, so IP matrix, IP mat, relative clauses, IP rel, noun phrases, adjective phrases, adverb phrases, and preposition phrases, and maybe a few more types of constructions. and most parsers are able to produce this kind of skeleton structure, but having parsers that give you more information, that they're much rarer. And I do want more information because I want to inform my students about interesting analysis. And really, a skeleton structure is a very underspecified structure, and is not really very useful for reaching full semantic analysis. So the additional information that I want to get my parser to produce is going to be codings of grammatical function information, so subject and object. I also have, so these are kind of obviously familiar terms. I've also got this CLR. So this stands for closely related element. And we'll see some examples of closely related elements when we look at some examples. And there's also this NIM, which stands for I don't know, not important, or not a selected item. So these are going to be items that are adverbial in nature and are not essential components for the sentence integrity. So whereas these guys are kind of core essential arguments that are going to be well, that are needed, expected. Okay, so I also want to have zero pronouns as not zero pronouns, as zero elements. So I want indexing for unbounded dependencies, and I want traces for relative clauses. Okay, so that's my kind of what I want. The approach that I'm going to take is really a real retro approach. I'm going to be using definite clause grammars, which were kind of invented back in 1980. And I'm going to be using the XSB tabling Prolog system to actually run the DCG grammar. So DCG, if you're not familiar, it consists of a Prolog program for parsing content given with a difference list as input. So a DCG is basically written as phrase structure rules. But these rules are enhanced with syntactic categories, and the syntactic categories are Prolog terms themselves, which are able to take extra logical parameters, and that's really the power where the system gets its power from. So the Prolog terms of a DCG can correspond to complex feature structures found in theories like generalized phrase structure grammar or HPSG, the kind of things that Yusuke was showing us with his percolation of information. And so this is used to pass on unifiable values such as selection criteria and records of long distance dependencies. So the approach is very classical, the Prolog terms. So Prolog terms can also accumulate the structure for the parse. So that's how we actually build the parse tree as well. The XSB implementation is really very special in that it allows phrase structure rules to include left recursion without infinite loops arising from the rule evaluation, which means you can basically write any phrase structure rule without having to worry about nasty consequences like infinite loops, which was always the problem back 20 odd years ago. Okay, so to give you an idea of the kind of rules that are created, so here's a very simple rule for the utterance level of interpretation. The utterance level of the parse. So this is basically a rewrite rule that's saying I found an utterance if I happen to have found content for a clause top layer and a punctuation. And then the information that's kind of gathered from parsing these components are then integrated together, and a Prolog term is used to create the actual parse result with the univ operator from Prolog. Okay, so that's really how all of the rules are written. okay, so here's an example of how you can interface with this during a prologue session. You basically spell out the words and the part of speech analysis, the word class analysis, and you say parse this as an utterance. And here's an example of a result. Here, the EX2 is just a kind of ID that's carried over. Okay, so that's kind of how you can interface with under the prologue kind of system. So it's really great. We've got this really quite amazing parsing engine, and the goal then is to increase the coverage and hopefully reach unconstrained English. And one of the problems that raises is how do you deal with the proliferations of parse ambiguity? That's the real Achilles heel of this approach, because this is very much a deterministic, well, this is very much a kind of generate every result kind of non-statistical approach. Now, classroom experience suggests, or at least my classroom experience suggests, that creation of word class analysis is something students can do really well, because they already are well drilled into determining what's a noun and what's a verb and what's an adjective and what's an adverb. But in contrast, creation of full parse structure, that's a real major challenge. So until I had the parser, I was kind of teaching the students to create these parse structures, but we didn't get very far in a semester. So the idea that I'm kind of following here, yeah, is to unite the strengths of both the human word analysis that I can get from my students and this automatic system that's going to create the disambiguated, to create structures from disambiguated word information. So that brings me to motivating the word analysis, so the human touch. So here we've got a just a sentence, whatever word you want to map in here. So the first word is a noun, the second word I'm saying is a noun, and the third word I'm saying is a past tense verb. And finally, we've got some punctuation. And there are really two compatible structures to this as an input. So if all we're doing is giving words with word class information, then we're going to be generating both these results off of this input string. So, and really, I'd like much more disambiguation to be going on, because this is a very simple sentence, and obviously, if you look at longer sentences, it's gonna the combinatory explosion is going to massively increase. Okay, so the extra information that I want to be adding is these grammatical codes. So two examples of grammatical codes that we can have are a marking for an intransitive verb and a marking for a monotransitive verb with noun, phrase, object. And if you do that to these the example we saw in then you get an unambiguous structure, because cheese pizza's smell is going to give us a structure that's looking like this, and cheese people smell, with smell as a transitive verb, is going to give us this structure where the cheese is a topicalized element. Okay, and so we can I have a parsing system that it's an online parsing system. It's available at this URL, which is kind of in the handout. So if we paste in this example, then we should get the parse result. Bingo, cheese pizza smells, and that's great. Incidentally, one of the reasons why the input is like this is because initially when I kind of gave it, the students were putting spaces in really awkward places. and one of the really nice benefits of using this kind of format as with the square brackets is you get to know the ending of where the word class information is, and so no matter where you put the spacing, now you always get a parse result. So that kind of solved a big bunch of headaches for lots of my students. Oh, okay. So let's yeah. So these grammatical codes, they're actually very interesting. So a large number of my codes that I'm using are sourced from this dictionary, the Oxford Advanced Learner Dictionary, but the 1989 version by Cowie, and this is attractive because these codes are this ambiguation information is linked up with word sense meaning. So I have an example here where, well, this is cheese pizza smells. So here we've got it analyzes in transitive verb, and bingo, we get to isolate the correct sense. If we go to the alternative analysis, we see that there's the flip side where we get the alternative sense. Ugh, I've only got 15 minutes left. Oh dear. Okay, so now I want to actually show you. So I said already that this parser can really do really quite wonderful tricks. So let's show you an example which is much more interesting than the previous example that I showed you. Let's parse the director who I think has a 15% holding and who is believed to be waiting to buy another steak. So this is a noun phrase by itself. So we want to have this analyzed deriving as a noun phrase. So let's stick in the analysis into the parser, and we get the result almost immediately. So we see that the whole thing is being analyzed as a fragment, which is exactly what we'd expect, because this is a noun phrase on its own. And then we've got the director is the head of the noun phrase, and then we've got two conjoined relative clauses. The first one is involving a long distance dependency. So here we've got an index being created by the system, which is then giving rise to this interpret constituent here node here to mark the unbounded dependency. And if we go over to, yeah, and so we can see here that we've got TF. So this is a grammatical code that's saying I want a transitive verb with a finite clause as my complement. So this is why we're able to mark this information as an object one. And again, we've got a transitive verb, this time taking a noun phrase complement. And again, this is enough information to tell me that this is an object. If we look over to the next part of this conjoined relative clause, we have another relative pronoun here, which is immediately being interpreted as the subject of this relative clause. Then we've got some information that this is a catenative instance of present tense be, which is giving rise to a catenative complement that is a passive participle with believed, so hence the logical subject information. And so this if we start looking at the semantics, this guy here is a syntactic subject here, but it's going to kick over into being the an object in believe. But this code here is very interesting. This is a TNT code. So this is a transitive verb that takes a to infinitive as its object complement and a derived object as its, and also a derived object. So something that's going to not actually contribute an argument to believed, but is going to contribute a subject via control to the object infinitive here. So our subject here that starts off, our thing here that starts off as a subject is kind of clicked over to being a derived object with respect to believed, which is then ticked over to being a subject inside the infinitive clause, and will then go on and be a further subject to by control. And if we kind of look at the, I said already it's a toolkit, so there's other components, and the other component there is this semantic calculation. So if we then send this parse, which we're quite happy with, through to the semantic calculation, we can see that all of these dependencies that I just spoke about, where we have so here we've got the director, who is, so this is the fragment level of the attachment to the rest of the clause. That's what this red line is telling us. We've got the role of the director as being the subject of the has 15%. And we've also got it, this is believed to be waiting, where the subject, so what is the syntactic subject for is, actually goes through travels through the structure and ends up as the subject, because it's arg0 of waiting, and furthermore goes on to being the subject of by. So you can see, I hope that this is illustrating that, you know, I'm getting an awful lot of really interesting dependencies fall out of this system. And it's also giving me a system that gives me very, constrains the ambiguity massively. So even though this is, you know, a very complex sentence with lots of potential for ambiguity, there is no ambiguity in the result because of the constraints that the language is enforcing on the available structure that can completely satisfy all the criteria of the grammatical codes and the underlying grammatical system. I think I've run out of time, so maybe I should stop there. Thank you.
Thank you very much. So we have about 9 minutes for questions and discussion.
Alastair, I just must say that I'm very impressed by two things. So the first, that DCG parser is, well, it's exponential, right? It's known to work.
Yes.
I mean, slow, right? And it seems to be even the sentence that, you know, barely fits on, I mean, or two sprints, it's, I mean, seems to be, I mean, handling it. So it's one impressive thing that I think worth elaborating. But another thing I find even more impressive is that what we ended up with, you say if you have, so to speak, part of speech more or less precise, a little bit extended part of speech precise information, then you don't need to have any well, you know, CCG, there is a lot of sophistication in the current parsers, right? I mean, to reduce. And then what your claim seems to be that, I mean, given, I mean, a good part of speech with particular extensions, then all of, at least in this example, all of this ambiguity disappears, and just do the, I mean, DCG is the dumbest thing that you can possibly do, right? Write a parser, just test and, I mean, generate and test, right? In a sense, that's what prologue. So it means that all the sophistication people are putting in this, I mean, I know CCGs and other parsers is actually not necessary if you haven't get correct marking. And correct marking you can possibly get with super tagging, right? So maybe we should invest more in super tagging than investing into all this, I mean, sophisticated parsing techniques. Would it be a good claim to make?
Yeah. I mean, basically, yeah. If you can get the base right, then pretty much everything else fits in.
Okay, it's actually, I mean, I think, I mean, and I really want you to kind of, I mean, write paper for the like parsers, because I think it's a very interesting result, right? Because
yeah, yeah, yeah.
to
Okay.
focus on a totally different direction rather than what we've been
Okay.
focusing before,
So
right?
that's a good thing. That brings me to, I have documented this, parser. In fact, I've written a book about it.
Oh, wow.
So
It's
yeah.
it's in your, is it linked somewhere?
Yeah. I mean, if you follow the parsing, it's linked.
Okay.
If you go to my website, you'll see links to it.
Okay.
So this is a book that kind of goes through and describes all of the things that you know, I've shown here, and shows the coverage. I also have lots of examples. That's another thing. Here there's hundreds of examples displaying really very complicated things that people in the past have. Yeah. Anyway, and to show that it really scales, here's a short story by Aku Tagawa. It's translated into English, but also translated. Given the word analysis, and you press the parse button, and bingo, you get the right parse.
Okay, then we have a question from Jimmy. Yes, please.
Okay. Can you show the active form of believed sentence?
Yeah.
Is it easy?
Yeah. What do you mean by active form?
Believed that. Believed that.
Yeah, of course. And that becomes a different code. It would become a TF code. Yeah, but there's lots of things you can do in terms of another thing that I haven't been able to stress yet is you can get really nice grammaticality judgments to fall out of the system. I've lost all my things. I'll try parsing in English. That's what I want to do. Here we saw an exact, the same example. Here we've got is that's giving rise to a past participle environment. If we change is to has, then that will want to be when it's be, it's giving rise to a passive participle environment. Where if we change this to has, then this will give rise to a past participle environment. But then the subject is going to be the real subject of believed, and we need to add in a derived object. So if I change this believe, if I change the is, which is here, into has, and I change the code into HVP, which is the code for have, and I try and parse, I get no result. Yeah, and that's exactly what you'd expect, because actually believed requires this derived object. So if I now stick in the derived object, which comes after believed, so if I say I had something like who has believed John to be blah blah blah, then so I stick in John and I parse, then bingo, I get a parse back, because now this who is being interpreted as a subject, and I've got my derived object. And if we look at the semantics, we get a very different story where now we've got the director contributing the subject, and we've got John being the derived object, which goes on to control as the subject of waiting and the subject of by. So you get these really nice grammaticality effects. So this is a real advantage of this system of not having a statistical component, that I get these very, very crisp consequences for the input that my students generate. And so I have a real way of testing whether they've understood the consequences of the grammatical codes that they're playing around with.
Okay, thank you. You used prologue, right?
Yes, correct.
And how would it compare to Python, for instance?
Oh, it's a million times better. Of course. I couldn't imagine doing this in Python. Prolog kind of makes everything really, I mean, you're just writing a very simple context-free grammar, essentially, has some additional information or ability to carry around information. But this is incredibly simple. It's yeah.
Thank you very much.
Okay, we have 1 minute left. So maybe a quick question.
So Oleg seems to be trying to force you to claim that this is a better thing than CCG parsing. I think that's an interesting position to try to defend seriously. But I was wondering, like, on a question from some of the opposite direction. So, what, as compared to dependency parsing, like how would you defend your own approach against dependency parsing?
What do you mean by defend?
Like people, like, I mean, there are a lot of people who do UD parsing on various languages.
Yeah, but none of the connections that I've shown you today are possible under a universal dependency. Like I showed you really complicated control relationships that are not coded, but also the problem with all of these kind of other parsers is that they are statistically kind of generating stuff, and they lead to sometimes the right result, but not in most cases they don't. And I, my purpose here is language teaching, yeah. And I want my students to get to good results, and my students don't have the sensitivity to know this is a bad result. So other parsers that I know of that are indeed kind of very famous and have big followings, they're utterly useless in the classroom situation.
I see. Yeah, I think I see your point. Sounds, yeah.
Okay, so we were out of time. So let's start to speak again.
Thanks.